Welcome back. So now that you know how to use vectors in 2 dimensions, and we've looked at a problem, conservation of momentum, for example, where we had our robots going in multiple dimensions. Now we're ready to apply that to a little bit more complex problem. If you recall, we've taken some time where we had a robot coming up underneath and then we dropped a rock on him, and we used free fall for that. Basically, the only force that was acting on the problem was gravity. But we could only do it in 1 dimension, so we had to make sure that the enemy robot was directly below us before we could do that. Well, what if we want to hit him from a distance? What if we want to launch across this way and still hit him? How will I find that downrange distance? How far will my projectile go based on the angle that I'm using to attack with? That's what we're going to look at now. And the key to all of this is that we're going to have to break our problem down into a horizontal component and a vertical component. And those two parts to this, both our horizontal and our vertical component, they're going to be linked by this idea of the time. That's generally what's going to happen in these kind of things. Remember, they're treated like separate problems, horizontal and vertical, but they are still the same physical situation, and it's going to be that time that's going to link them. You'll see what we mean as we get into this. Let's get started. All right, so let's take a look at this scenario. So what we want to find is the distance that our projectile will travel down the range, down the horizontal distance, and then we also want to know the time that it would take to do that, because with those two pieces of information, now we can attack our enemy battlebot from a distance. So our scenario is to find the horizontal distance and the time of impact. Right? And as always, we're going to want to draw a picture, and that's especially critical in this case, because you're going to find that you really can't solve it unless you draw that picture. So here's our ground, and this will be our launcher robot, and he's got a spring cannon that's at this angle that we're going to give to you in just a second. And he launches his projectile, and it comes out with some sort of an arc until it hits the enemy robot. So that's our situation. That's what we're trying to do. So we're told that the muzzle velocity, which we'll call Vm, is 2.50 meters per second at 35 degrees. Now we need to be really careful about where we're specifying that angle from. Remember from the last time, you have to specify a reference direction from which you're going to start measuring. So in this case, we're going to measure it from the horizontal. So 35 degrees from horizontal. It is perfectly okay to measure from the vertical to there. And in fact, as we mentioned here with rockets, that's the norm. Normally your rocket's going to go straight up, but often you'll give it some initial angle, and you're going to use that vertical angle rather than the horizontal angle. There's not a thing wrong with it. And as long as you're careful, it's not going to matter, but you do need to specify it. And so the best place to do that is in your velocity description here, in your magnitude and direction format, and then also in your picture. So this is going to be 35 degrees. Okay, and then this direction is my Vm. And that's still a vector. All right, so what we want to know then is we want to know this distance. That's going to be our total horizontal distance, and we don't know what that is. And that's going to be in meters. And we also want to know the time to impact. And we don't know what that is either. Okay. All right, so the next thing we have to do is we have to design our solution. And really when we say that, what we mean is what are we going to do? How are we going to approach this? For this. And this is really important because once you get out in the real world, this is your job. Your job is to figure out this design. How are you going to approach this situation? And then you're going to have a team that's going to help you actually go through all of the steps. But your expertise comes in figuring out how that approach is going to take place. So even though you may not totally feel comfortable doing this yet, it's time for you to start kind of brainstorming how you're going to approach the problem. All right, we're going to kind of walk you through it this time. So we need to figure out, there's actually 2 phases to this problem. Can you figure out why? Well, think about it. If I start here with my vertical and I end here with my vertical, right, then I haven't moved, have I? And so there's no kinematics equation or anything that's going to give that to you. Instead, and we'll use a red line here, instead I'm going to have to break this down into two phases. And so our first phase, so our phase 1, is going to be from launch to apogee. Now, I don't have to choose apogee for that, right? However, I know something, I have some additional information at apogee. Do you remember what that is? My velocity at that point is going to be 0, right? So that's a good break point. That's a good point that I could easily divide that, because now my final velocity at apogee is 0, which means my initial velocity from apogee to impact is also 0. So from phase 2, we're going to have from apogee to impact. Okay, and as I was saying, the thing that's going to happen is this final velocity, this velocity at apogee, that is my final velocity after the launch phase. But then that same apogee velocity is going to be my initial velocity for this phase, for the apogee to impact phase. And so that's going to connect us in there. Okay, so that's our basic idea. Right? Turn over to the next page here. All right, so now let's start designing our plan for our first phase. And we said that our first phase was going to be from launch to apogee. Let's resketch that part of it. So this is going to be our j-hat direction. This is going to be our i-hat direction. Remember, since I'm putting my j-hat here, we're assuming that up is going to be positive, and this way my I is going to be positive to the right in this case for the horizontal component. All right, I've got an initial velocity here, and I'll write that over here. We call that Vm, and this is a vector, and we said that it was at 35 degrees. And then the projectile comes up here to apogee, which is also a vector. Okay, and so this is the first phase. All right, so I want to get the total downrange distance. So we decided that we could get this part of it, and we would call that dap. So the distance that it goes in apogee. And this is strictly in the i-hat direction, right? There's nothing in the vertical direction at all. Okay, so let's think about what we might do then to solve this. Well, as soon as it leaves the cannon, what is the only force that's acting on it? Well, gravity, right? So it's in free fall. And so is gravity constant? Well, no, not really. However, between our apogee height that our robot can reach can send its projectile on the floor, it's not going to change enough that you can measure it. So we can treat it as a constant for that. So we're going to have a force due to gravity here, and that's going to give us an acceleration. Now, I don't like to write embedded vectors here until I know my signs and all that other sort of stuff. And in this case, we know that it's going to be in the minus j-hat direction. So this, my acceleration in the j-hat direction, let's just get rid of that arrow in between there. My acceleration in the j-hat direction then must equal minus g in the j-hat direction. And this, of course, is a vector. All right. So we want to get the horizontal component. So if we've got a constant acceleration, what did your brain scream? Well, you're going to use kinematics, right? Always going to use some kind of kinematics. But we might have a problem here. We want to know the vertical acceleration. I'm sorry, we want to know the horizontal acceleration. We already know the vertical. This is the vertical. We've got that. Is there any horizontal acceleration? So my question is what is the horizontal direction? Well, there is no horizontal acceleration. That's 0 meters per second squared, right? Well, that's also constant, so I can certainly use kinematics in this case. However, if I want the distance, how am I going to get that? Well, I've got some velocities. Okay, maybe that'll get us there. So we might say, we're just sketching at this point. Our final velocity is going to be the i-hat direction, right? And then that's going to equal our initial velocity, which is the i-hat component of that. Let's make sure we're clear on which one is I and which one's j. This vector here, this red vector, is going to be Vm j hat, right? And then we'll do this in green. This vector here then is going to be Vm I hat. or you can write it as just VMI. It's fine. Okay. So this is our VMI, and we can figure that out because we know how to break things into components. All right, well, if I wanted to use the position versus distance, or sorry, the velocity versus distance equation, these things are squared, plus 2, and this is the A in the I hat direction, and then our delta x is going to be our DAP, which is also in the I hat direction. So everything in this equation has to be in the I hat direction. I can never mix them in between. But what is the acceleration in A? Well, it's 0. So I'm left with VAP in the I hat direction is actually equal to VM in the I hat direction. Let's clean that up just a little bit. So that's VM in the I hat direction. Well, that's useful. That tells us that the horizontal velocity doesn't change, which we knew because there was no acceleration in the horizontal direction. Since there's no acceleration in the horizontal direction, remember acceleration is a change in velocity, then that velocity has to be constant all the way across. So that's good, that's information we can use, but it's not going to tell us how to find that distance. So now we've got to think about other possibilities. Well, okay, what else do I know in the horizontal direction? Well, I want to know a distance. Well, what if I had, we'll write it in our general root form here. That would be plus VIT plus 1/2 AT squared. Now, let's make sure that we're setting everything to be in our vertical direction, and we'll start substituting in our actual distances. So I'm starting from 0, so that one's certainly 0. And then XF, my horizontal, since I'm dealing with the horizontal component here, all these are going to be I's, I hats, that is. I hat and I hat. So that's going to be DAP, which, by the way, is in the I hat direction. Well, that's going to equal my initial velocity, which in the horizontal direction is VM I hat. And it's going to be positive, so we could actually get rid of our vector sign and write it out explicitly. That's probably going to be very helpful. You see that that's still a vector. I've got my magnitude, my direction. All right, times t plus 1/2 AT squared. But what is A in the horizontal direction? Well, that's going to be 0, right? And so this is what I'm left with then. Well, I know my initial velocity, or at least I can get it because I can break that velocity down in components. I want to know d. So this is telling me, the problem is saying, hey, go find the time. And this is going to be very common. Anytime I'm using these two-dimensional problems, time is going to be the linkage between my horizontal and my vertical part of the problem. Remember, those are completely separate problems, but they share the same time. See if you can figure out why. We'll do this in purple here. So the time for that projectile to get from the ground to apogee must equal the time that it takes to get to D, my distance horizontally at apogee, right? Because it's moving together. So very often that's what we're going to do. Here the problem is telling you, go find the time. If you find the time, I'll give you what you want. I'll give you that distance. So we know, though, that usually to find the time, I'm going to go over to the other side. All right. So what I would do then is I'm going to say, okay, I need to find out my time. So my phase now becomes find the time from launch to apogee. So I'm breaking this down into a new problem. And that's really what you want to do. Instead of trying to solve this whole massive, complicated problem at once and trying to hold the whole thing in your mind, focus on one piece at a time. That's what you're going to do in the real world. Most projects are too big for one person. You're going to be working on a team. And so you're going to focus on this one smaller bit. And so that's what we're learning here. All right, so I want to find, I know my velocities, right, in my vertical direction. I know my initial velocity is going to be my VM j hat. And I know my final velocity is going to be VAP j hat. All right, so let's see if we can figure out what that is then. So which kinematics equation, I'm still using kinematics, right, because I still have constant g. which kinematics equation, if I know the velocities and I want to know a time, which one's going to give that to me? Well, that's going to be my velocity versus time equation, just like we expected. So I'm going to have my final velocity, which is v app, in the j hat component, and that's going to equal my initial velocity, which is Vm in the j hat component. Now I'm writing that as a scalar magnitude, and it is in the positive direction. What is V app j? What is the velocity of at apogee for this? So we see that at apogee, the vertical velocity is 0, but the horizontal velocity is not. And that's going to be one of the big things that's different. Remember when we were just throwing the ball up, it would go up here and it would have 0 velocity here at apogee. That's because the vertical component goes to 0. The horizontal component, though, there's no acceleration, so it doesn't change. It stays the same. So, and then this is going to be plus a in the j hat direction times t. Well, a in the j hat direction, we've already decided, is going to be minus g. So let's copy that then. We've got 0 is positive, vmj, and then plus a negative g t. Remember that my g is a scalar magnitude, so g is equal to 9.81 meters per second squared. Not positive 9.81, not negative 9.81. It's a scalar. It doesn't have any concept of direction. I've taken care of my direction here with that minus sign. And the reason you want to keep that outside separate is because I could very easily reverse my coordinate system and have down be positive, couldn't I? And then in that case, my acceleration is going to be in the positive direction. So always go back to using these scalar magnitudes. This is still a vector. It's got a magnitude and it's got a direction. So I haven't changed the fact that I've still got this vector here. All right, I'm going to bring my gt to the other side so it becomes positive, and that equals Vmj. Both of these are positive. And then I know that I'll be able to solve this, and I'll get that my time, and we'll call this the time to apogee, is going to equal Vmj, my initial velocity in the j hat direction, divided by gravity. So we went ahead and did a little bit of the math here because we're kind of brainstorming. And eventually what you're going to do is, rather than separate these out into individual components like this, you're going to kind of go off and say, okay, what can I do with this? Will this get me there? While I'm kind of sketching out my plan. So now you see that because the time to apogee here is also the time to apogee here. So I'll be able to break it in components, get my vertical velocity, figure out the time, put that in here, multiply it by my horizontal initial velocity, and that's going to give me my distance. Okay, so let's summarize that. So first thing we're going to do is we're going to break it into all our vectors into components. So we're going to break all vectors into components, and that's going to be true pretty much every problem you solve. The very first thing is you're going to break all those vectors into components. All right, and then now we're just talking about launch to apogee. So I now know I'm going to find the time to apogee using the vertical side. So I'm going to use the vertical components. And then once I have that, I'm going to find the distance downrange to apogee, not up. I'm talking about the distance across, using the horizontal component. Okay, so that's my plan. So that will allow me to solve step one. Remember, I want to know what these two different pieces are going to be. Now remember, the problem also wants to know the time for it to go across. Well, we've also, as a bonus, we have found the time for it to reach apogee. So that's going to be something that's going to be worth writing down. All right, so let's record our symbols here so that we can go ahead and get started on this piece. So we know that we have Vm as a vector is going to equal, let's see, I forgot what we said. It was 2.5, yeah. So it's going to be 2.50 meters per second at 35 degrees from horizontal. Okay. And that's all the initial information we were given, right? We do know that our j hat component is going to be equal to minus g in the j hat direction, and we know that that's a j, and we know that our I hat component is going to equal 0 meters per second squared. Okay, so let's break these down into components. Oh, I'm sorry, one more vector up there. Our apogee velocity is going to equal 0 in the j hat direction, but it's going to have some velocity in the horizontal direction. So you could break that out. It's easiest to write it in components. I know that this is going to be VMI in the I hat direction plus 0 in the j hat direction, based on what we've kind of brainstormed here. Pause for a minute and see if that makes sense to you. Kind of pause the video and go back and look and see if you can figure out what we've done. Based on our brainstorming, this is what we've got. All right, so this is a good place to break down our velocities into vectors. We've already done one of them. That one was easy. This one we're going to have to use some trig on. All right, so if I want to find the I hat component, because we've already figured out that we're going to need that, right? Then let's draw that triangle for us. Here's our VM. This is my I hat component. So that's VM I hat. And this is going to be my j hat component. So VM j hat. So just zooming in on that little picture that we have up there. And we know that this angle is 35 degrees. Well, and remember, I need my angle to be inside my triangle. So I'm going to slide this side over like this. So this is VMJ. That's how I choose which side to slide over, so I want to keep that angle inside. All right, so VI, is that going to be cosine, or is that VMI, is that going to be cosine, or is that going to be sine? Well, cosine is the adjacent over the hypotenuse, so that one's going to be cosine. And so what I have is that cosine theta is equal to my adjacent side, which is VMI, divided by my hypotenuse, which is VM, and those are scalar magnitudes. And so VMI is equal to VM cosine theta. So we could go ahead and put that in there. This is going to be 2.50 meters per second times the cosine of 35 degrees. So let's go ahead and work out a number for that. Pull out your calculator. And so it's going to be 2.5 times 35 cosine. Make sure your calculator is in degree mode. And when I did this, let's make sure it matches my earlier results. So we have 2.5 times 35 cosine equals, and I am getting 2.0. We'll go ahead and keep 4 significant digits for now. We'll have to round off to fewer meters per second, and that's in the I hat direction. While we're at it, let's go ahead and do my j hat direction. So that's mj, and that equals 2.50 meters per second. And you can probably guess that it's going to be sine, but let's verify it. So the j hat direction is this one, and so that's going to be the opposite over the hypotenuse. So sine of theta is going to be the opposite, which is vmj, over the hypotenuse, which is vm. And so we'll just write it over here. Vm is equal to, or I'm sorry, vmj is equal to vm sine of theta. So times sine of 35. So let's do that one then. So we get 2.5 times 35 sine, and I get 1.3434 meters per second j hat. And remember, we don't have 4 significant digits of precision. We're going to have to shorten that, but it's okay to keep some for your intermediates. All right, so we now have everything that we need for our initial values. We could, on the next page, we're going to have you copy down your equations for that. And so the equations that we're going to use are simply going to be basically this one and this one. This one tells us just that the V apogee is the VMI. That's how I was able to get this right here. Right? So that one doesn't add anything useful to it. But these two equations here are going to be what I'm going to write down in my step 4. All right. So while we're on this step then, let's go ahead and erase this, and you can always go back and look at the video if you need it, because now we need to look at the second phase. And so the second phase of our work, we're going to go from apogee to impact. All right, and we've got a whole lot that we've got to erase here, because I really don't want to redo all of my breaking into components, right? I've already done that, so that's going to be the same. Notice that I've not used any VIs, V initial and V finals. The reason for that is, remember that the initial velocity at apogee, or the final velocity at apogee, is my initial velocity for my next phase. And we've had a lot of problems where we've done it that way, right? So it's a good idea to think of that VI and VF in your flipbook, in your list of equations and everything. That's a shell. And then never use the actual VI and VF. Always define a symbol that's going to give you what you want for that, because that'll avoid confusion as well. Okay, this is VI, but it's actually VF, right? That's going to be really confusing. All right, so now we've got this thing erased. Let's go ahead and draw us a new picture so that we can follow what's going on. And so this is going to be for the second half of the problem, the second phase. And this is going to be from apogee to our impact. So let's draw our coordinate axis here. We have to keep our i's and j's in the same direction. Once you set it, you can't change it. So our initial here is going to be this vector v apogee. And now it's coming down here, and we're going to hit right here. And we don't know that velocity, do we? We don't have any initial conditions for that velocity. But what I'm looking for nonetheless is going to be this distance to impact. So that's the distance from apogee to impact, not the total distance here. All right, so let's think about our vectors here. Now, at this point, we've already decided that my j-hat component of my apogee is going to be 0. So I know that my vector is going in this direction, right? All right, and I want to know how far I travel in the time it takes for me to get to the bottom. Well, on first glance, it looks like I don't have enough to solve that, do I? I don't have any times. I don't have any any velocity. I don't have a final velocity. All I have is that initial velocity. I do have an acceleration in the two directions, but I don't actually seem to have enough. Now, you may instinctively say that the time from launch to apogee has to equal the time from apogee to impact. Because remember, we did that when we were launching straight up. The time from here to here is going to be the time here. And if there are no other forces involved, if it's truly in free fall, that's true. It is going to work out that way. But what we want to do is we want to work out a method so that if I add things like air resistance or friction or any of these other forces, in which case then the time up is not going to equal the time down. So what do we do? All right, so we're going to take it a little bit on the long way then. So if I have my initial velocity here and I have a position here, okay, I don't have the final velocity and I don't have any way to get the final velocity, but I do have a way to get the height of apogee, don't I? Not from this problem, but from the previous problem. So if we look at our height here, right, that's still the height to apogee. And I know the time it took to get there. I even know my velocities. So I can use either one of my equations. I can use my vertical equation here. This is going to be j hat. I can use my vertical side to figure out what that height of apogee is going to be. Okay? So that's going to be our plan. Let's make sure that makes sense to you. If I can get my height from the horizontal side, or sorry, from the phase 1 side, which is launch to apogee, then that's also this. Now do you see that you could actually get that distance? It's going to take 2 steps to get there, right? So I'm going to first need to know, what is my time in the vertical direction to fall? What is that time? Well, that time, remember, is my link, and so that's also going to be my time to go across horizontally. Once I know my time horizontally, I know this. I already know my horizontal velocity. My horizontal velocity isn't changed, is it? So this is still going to be VMI. It's not going to change at all. So that's going to be our plan. Let's go ahead and write it out, though. So from apogee, let's spell that correctly. So we're going to go from apogee to impact. Okay, we've already broken our vectors into components, so we're good with that. And so what we want to find then is we want to find HAP from phase 1. Once I have that, now I can move over to this side, to the phase 2 side, right here. And I can say, okay, find T, we'll call this T impact. That's the time from apogee to impact from the vertical part of phase 2. And just to remind ourselves, my height is obviously in the vertical direction, but let's go ahead and make that explicit. So from the vertical direction. Okay, once I have that time, then that's going to allow me, I'm going to have my time from here to here. I'm sorry, this one from here to here. That's going to be the same as my time for my horizontal. And so we're going to find d impact, our horizontal distance, from the horizontal part of phase 2. Okay, so that's the plan. All right, so let's think about symbols that we're going to need. We're going to need to find my height of apogee, and I don't know what that is. And I'm going to need to find my time to apogee, and I don't know what that is. And then that's going to give me my d to impact, which is going to be the last thing that I need there. And just for completeness, we'll put up here that we also need d to apogee, because I'm going to need to add those together, right, to get my total distance. Okay, so now we've got a plan. Now we have an idea of what we're going to do. All right, having done that, then we are ready to go ahead and start solving this problem. All right, now that we've got our plan, we've got our initial variables laid out, we're ready to actually start writing down our equations. And we're going to stay with the plan that we had. And I find it useful to remind myself whether I'm working with the vertical component or the horizontal component. Now, eventually, you're going to read all j hats as a vertical component, and you're going to read all I hats as the horizontal component. But you might not be there yet. So let's go ahead and give ourselves a little extra bit. So using the vertical side, let's see what our situation is. And then we're going to break it here at apogee, or as close to apogee as I can draw. All right, so for my vertical side, our plan was to find t, the time to apogee. And we were going to find that using the vertical side. So I want to know the time to get from here to here, or thinking of equivalently the vertical side, I'm just going from here to here. If that were actually up at the same height, of course, like that. Okay, so I want the time from here to here. That's going to be my time to my apogee. Okay, so we know velocities. We don't know a height yet, but I know a time. So which of the kinematics equations am I going to use? I'm going to use velocity versus time. That's why we named it that. All right, so writing down that equation, it's going to be my final velocity, which is v ap j, is equal to my initial velocity, which is vm j, because we're only talking about in this vertical component here, plus my acceleration in the j hat direction times my time for apogee. And we know that this one is 0, because only in the vertical component is my apogee 0. So this is my v ap, remember? So it's got no vertical component, but it does have a horizontal component. All right, and so you see that, and then of course, let's remind ourselves that a j is going to be minus g, and a I is 0. So my only acceleration is going to be in the vertical direction, and that's going to be minus g, and then I have no acceleration in the horizontal direction. All right, so the next thing we were going to do then, what we really want is this d ap. We really want this distance here, because we're going to add that to the other side. So we're going to use the horizontal component for that, and hopefully that you can see why, because, well, I'm traveling horizontally. So I'm going to use the horizontal component for that. I want to know a distance, and I've got a time. We decided that that's how we were going to do it, so I'm going to use the distance versus time equation. So my final distance is going to be d ap. My initial distance for this phase is going to be 0, plus, and then I'm going to have an initial velocity, vmi, times t ap, plus, and then the acceleration term, I t ap squared. However, remember, that's 0. Okay, Now that's actually all that we need to find dApp. So that would solve completely our first part, to find the distance from launch to apogee. But if you remember, when we were trying to find the apogee to impact, we realized that we're also going to need hApp, aren't we? You see that? So what we need to do then is we're going to get that then out of our launch to apogee phase, because that's the only place that I know the values I can do it, right? I know my time. I know the time that took here. I also know my velocities, so I can know my distance. Well, I would rather not use the time, because if I made a mistake in calculating that, then I'm going to have a mistake in my height that I'm calculating as well. So it's okay to do that if you want, but why not go back to something that only uses initial conditions? So we're going to remind ourselves that we're only using the vertical side here. And so let's use the velocity versus distance equation. So my final velocity is vapj, and of course that's squared. And my initial velocity is vmj, also squared, plus 2 times my acceleration in the j hat direction times the distance, which is hApp. You see, that's what I'm traveling in the vertical direction. Okay? So that's got all of that. Remember, our goal was to get this hApp, because I'm going to need that for the other side, we decided. Okay, so let's do that then. So now for this side then, we're going to try to find, I want to know this distance here, which we are calling the impact. Okay. And so I need to know my time then. I don't know the only velocity I know it's here, the initial velocity. I don't know my final velocity. So I don't have that. I do know the height, and I know my initial velocity. So if I can get the time then, I can use that to get what I need right here. So let's figure out the time for it to go from here down to here. Okay, so we're coming back down. Now, as we said before, you know that these two times are the same because I have no other forces. So you remember when we were throwing it straight up and then straight back down, the time up was going to be equal to the time down. And that's going to be true here as well. However, instead of just setting them equal to each other, remember we want to go through this procedure so that later if I'm adding air resistance, for example, then my time up is not necessarily going to be equal to my time down. There's going to be a lot of other forces that I can add in here. So let's go ahead and using the vertical side. All right, and we're going to use our hApp to find the time impact. So I'm going to use my distance versus time equation because I have a distance and I want the time. So our final is actually going to be 0. I'm hitting the ground. My initial is going to be hApp. And then my initial velocity in the vertical direction is going to be vapj. And that's going times this time impact, which is what I'm looking for. And yes, we know that it's the same as my time to apogee, but we're pretending we don't know that. Plus 1/2 vertical component aj t impact squared. Okay, now this would be ugly except for the fact that, remember, at apogee my vertical component is going to be 0. All right, so now we go to our horizontal side, and now I can get what I actually want. I want to find d impact, so I'm going to find that given the time of impact. So I want my distance versus time equation. So my final distance is going to be d impact. Now the time that I'm talking about is the time from here to here. And remember, you can think of that in a number of different ways, but what I think the easiest thing to do is just consider these literally separate problems. And so now this becomes my 0. Do you see that what I've drawn in red here then becomes a completely separate problem from what I'm going to draw in blue here? I think that's the easiest way to hold it in your mind. You can do you, but given that, then if this is a completely new problem, then my starting point here, my initial point, must be 0. And I think most students usually see that a lot easier than why I might put in this dApp. Okay, so then I need my vApp, but now this is in the I hat direction, which is not 0, t impact. Because remember, we found that this is my vApp, it's actually in the horizontal direction. Okay, plus 1/2 ai, that's an I, t impact squared. But this one is 0 because I have no horizontal acceleration. All right, now we've got everything that we need from this. Okay, so let's go ahead and answer our quick questions here. What is the acceleration in the horizontal direction? Well, we found it right here. That's going to be 0 meters per second squared. And what is the velocity? So will the velocity in the horizontal direction change? No, because I have no acceleration. So my initial velocity is going to always be the same. My velocity is going to be the same everywhere that I get up here. So my app velocity here, let's make sure that we see that, are the I hat component of our apogee velocity must also be equal to the I hat component of my initial velocity. Now, if you don't see that, I mean, we should be able to see that because there's no acceleration, right? So if I have no acceleration, my velocity literally can't change. But what if you took one of our kinematics equations? Let's say that this was my final velocity, and this was in the I hat direction, and this was my initial velocity plus a in my initial velocity by some time that it takes me to move that distance. Well, if this is 0, then I've just proven that those two have to be the same. But that should probably have been obvious to you with that. All right, so now we've got all of our equations, we've got all of our unknowns. We're finally ready to solve the problem. Let's go to the next page. All right, so we're ready to start putting this together in our step 5 then. So looking here, this is where we wanted to get the time. And if you remember, our equation for that was that we were going to have V app J, which was our final velocity, is equal to Vm J, which was our initial velocity, plus AJ, which of course is just gravity, times T to apogee. So that's going to give me my time to apogee, right? Now let's go ahead and mark out things that are 0. We know that that one's 0. I'm going to remind myself that AJ is equal to minus J, and AI is going to be equal to 0 meters per second. And you've worked out the values for all of the constants, for all of the initial values on the previous page, so you can refer back to that. Okay, so let's use this then to find our time to apogee. And I'm not going to have enough space to do that over here, so we're going to write it out over here. So I have 0, oops, we can do better than that. So I have 0 is equal to Vmj plus AJ T app squared. Or I'm sorry, just T app. And I'm going to solve that for T app. So that gives me minus, cannot write on the screen today. That's going to be minus Vmj is equal to minus G, because that's AJ, T app. And so this implies that T app is equal to Vmj, positive, over G, because you see my minus signs cancel. So Vmj over G. And that's good because my time had better be a scalar. So there better not be a sign there. So that's going to be my time. All right, and I can work that out. And let's go back to our initial values here that we have on our notes page. We said that our initial velocity in the j hat direction was going to be 1.43 meters per second divided by 9.81 meters per second squared. Let's pick up our calculator and let's do that. So we get 1.43 divided by 9.81, and I get that the time is 0.146 seconds. See if you get the same thing with that. Okay, so now we've got the time. And so the next thing we wanted to know was we wanted to know the distance to apogee, the horizontal distance to apogee. And so if you remember the equation that we have for that, and you can look on the previous page, that was going to be distance to apogee, and that's in the horizontal direction. We started from 0 plus my initial velocity in the horizontal direction times the time to apogee plus 1/2 my acceleration in the horizontal direction time to apogee squared. And this one, remember, is 0 because there is no horizontal acceleration. All right, that one's going to be pretty easy too, so let's go ahead and solve that. So we'll put that down here, and that's going to give me d app is equal to Vm in the I hat direction times T app. which we know both of those. So let's go ahead and work out our numbers here. So we decided that VMI, going back to our initial conditions, pulling back that page, then was 2.05 meters per second times 0.146 seconds. 2.05, putting that in the calculator, and we get that DAP is going to be 0.299 meters. Okay, see if you get the same thing. All right, now we've got everything that we need for phase one. We were able to find, just from those first two equations, we were able to find our distance from launch to apogee. Now, for phase two, we're going to go from apogee down to impact, and we realized that we were going to need that height of apogee, and we were going to find that using the values from our phase one side. So that's why we wrote that equation down over there. However, what we want is to actually use that here. So let's write that equation down. Let's copy that equation down here. And so this again is from the phase one side. And so we have our velocity at apogee squared was equal to our initial velocity, our muzzle velocity, plus 2 times AJ, and that's also squared, times my height of apogee. So just using the position versus velocity equation. I could have used the position versus time equation because I found the time, right? We already know what that is. So if I had done that, then it'd be fine. I should get the same answer. But if I made a mistake in my time, I'm going to make a mistake here as well. So it's usually best to try to go back to something that uses your initial values. So we've got all these symbols here. Let's remind ourselves of what we've found so far. We know that AJ is going to be minus G. We know that the horizontal component of the acceleration is going to be 0 meters per second squared. We will just remind ourselves that VAP in the J hat direction, remember, was 0. And we know that our VAP in the I hat direction is equal to our initial value in the horizontal direction. And then the other things that we knew, the things that we derived here, we found that the time to apogee was 0.146 seconds. Now that should also be the time to impact. That's why we're using this, finding out the height of apogee. That should be the time to impact because there's no other forces involved, right? So the time up should equal the time down. However, if there are other forces, they won't necessarily be the same. So we want to have our technique so that we can just prove that in this case, yes, they actually are the same. But if it's not, we would know what that was. All right, the other thing that we found was the first half, our distance to apogee was, from launch to apogee, was 0.299 meters. Okay, so that's got everything here. All right, so looking at this, then we know that this term is 0. So let's copy this down over here. We've got 0 is equal to VMJ squared plus 2AJ HAP. All right, so we're going to move this to the other side. I get minus the initial velocity in the J hat direction is equal to 2. I'm going to replace my AJ with minus G HAP. I'm going to divide both sides. Oh, by the way, that's squared. Let's be very careful about that. Then we're going to divide each side by 2 times minus G. The negative signs go away, and I'm equal to the J hat initial velocity squared divided by 2G should equal my apogee height. All right, let's put it in our calculator and find out. So going back to our initial values, back on that very first page where we had our step 3, then we said that our vertical velocity, our initial vertical velocity, was 1.43 meters per second. And that gets divided by 2 times 9.81. By the way, that needs to be squared, don't forget. Meters per second squared. Because if you think about it, I need to get a height, so I need these second squareds to cancel from that. All right, so we put in our numbers then. We got 1.43 squared divided by 2 divided by 9.81 meters per second squared, and we get that is equal to 0.104 meters for our apogee height. And remember, the whole reason we wanted that was so that I could find the time from impact. So I know I'm dropping from this apogee height. Right? I'm starting here and I'm dropping. Let's just sketch that right quick so we can see that. I'm starting here and I'm falling that distance h-ap. Okay, so therefore, if I know my velocities, then I will be at my distance. I can now figure out what is going to be my time to get there, and that's what we're doing down here. Okay. All right, so we've got two more equations then that we need to work with. So we decided that we were going to use our distance versus time. Now that we've figured out our distance here, we can use that to find the time to impact, which should be the same, we hope. So we remind ourselves that my final height here is 0. I'm hitting the ground here, so this is 0. This is h-ap. So my initial height is h-ap. I'm dealing with the vertical time because I want to find the time for it to fall. And so that's going to be plus, remember h-ap is in the vertical direction, so I don't have any choice there. That's going to be v-ap j, because that's my initial velocity, at my initial point right here. Remember, distinguish between launch velocity, or muzzle velocity, and initial velocity. This is our initial velocity for this phase, times t impact plus 1/2 a in the j-at direction times t impact squared. All right, and you can confirm on the previous page that that's what we got before. This is still 0 because v-ap j is 0. So let's bring that down here. And so I get 0 equals h-ap plus 1/2 the j-hat acceleration times t impact squared. I'm going to bring this to the other side. And so I get minus h-ap is equal to 1/2. Again, I'm going to fill in my minus g there. T impact squared. My minus signs are going to go away when I divide, and so I get th ap divided by g is equal to t impact squared, and that should look very familiar by now. And so that tells me that t impact must equal the square root of 2h ap over g, which is square root of 0.104 meters times 2. Didn't quite have room for my 2 there, but you can see it, 9.81 meters per second squared. All right, pull up our calculator again. So we've got 2 times 0.104 divided by 9.81, and then don't forget to take the square root. And look at that, we got that our impact time was 0.146 seconds, which was exactly what we found for the time from launch to apogee. So we've proven it, that it actually, the time up is the time down. Just remember that that's only if there are no other forces that are coming into play with this. Now we've moved beyond our initial, let's just launch it up and launch it down. We can start adding more of these forces in here. All right, so I wanted to find my time so that I could get this distance. So remember, we're going to consider this a separate problem. So I'm going to call this my 0. My initial position is 0 here. And the reason for that is because my time started at 0 right here. You don't have to think of it that way, but I think that's the easiest way to think about it. So we want to find this distance, which is, remember, d impact. And so we're going to use our distance versus time equation. So our final horizontal distance is d impact. We've decided that we're going to start counting from 0, and then we'll end up just adding it to our d apogee to add in this piece here. And then that's going to be plus my initial velocity here, which is going to be v-ap j, I'm sorry, v-ap I, because we're in the horizontal direction, times t impact plus 1/2 ai, whoops, let's make that a vector, shall we? Times t impact squared. But ai, remember, is 0, so that term goes away. All right, we're out of space on the side, so we'll do it underneath here. So I've got d impact, which is what I want, is equal to v-ap I. But v-ap I is my initial muzzle velocity. We proved that, the horizontal component. And we've got a value for that. So we're going to go ahead and put that in there, times T impact, and this is just 0. All right, so finally we've got D impact. So D impact is equal to my initial muzzle velocity in the horizontal direction, going back to our notes, that was 2.05 meters per second. 2.05 meters per second times our impact time, which was 0.146 seconds. Let's put that in our calculator, and we get 2.05 times 0.146. And guess what? That also gives our distance is going to be 0.299 meters. Now that should not surprise you, right? Because there was no acceleration in the horizontal direction, it was moving at a constant speed. So in the same amount of time, it's going to cover the same amount of distance. Make sure that that makes sense to you. So my total distance then, and we are 100% out of space here, so let's just block ourselves off a little piece here. Our total distance then is going to be, our total D is going to be D app plus D impact. So I'm just adding those two pieces together. This time up plus the time, or the distance up plus the distance down. D total is going to equal 0.299 meters plus 0.299 meters. And we can go ahead and put that in our calculator, 2.99 plus 2.99, and that's going to be 0.598 meters. So now finally, we have everything that we needed, everything that we wanted for that. Let's go over to the next page. And so on the next page is where we did all that math that we kind of crammed down into that space there. I want you to see why, if I had chosen D impact to be the total distance from launch to impact, because that may make sense to a lot of you. In that case, if I'm doing this and I'm going up and I'm coming back down, but I'm starting my clock right here. So this is the time that I'm measuring from T apogee to T impact, right? For that phase of the problem. Then if this is 0, this is D apogee, and this then is D impact, right? Just all along that scale. So that's D apogee and that's D impact. So going back to my original equation then, if this D impact is my final and D apogee is my initial, right? Plus, then I'm going to have my V app in the I hat direction times my T impact plus 1/2 my horizontal acceleration times T impact squared. And of course, remember that was 0. So now we're going to come back and we're going to get that D impact is equal to, we found D app, look on the previous page, it was 0.299 meters plus V app, and remember that V app in the initial direction, in the horizontal direction that is equal to our initial velocity in the horizontal direction because there was no acceleration. It was staying the same. And so that we decided was 2.05 meters per second times our time to impact was 0.146 seconds. Pick that up, do it with me. Let's put it in the calculator. So I get 0.299 plus 2.05 times 0.146. And look at that, we get that D is also D impact, then using this method is 0.598 meters. So the only difference between them was the first way we did it, we set this point to be 0, and so therefore we were only finding this distance. On the other hand, if I kept this to be 0, then I would be finding the whole thing, but now I have to remember that this is my initial position. You do whatever that makes the most sense to you. Both of them work. As you can see, both of them are going to give you exactly the same answer. Now remember, there was one other thing that we needed. We needed to find the now so that we all know where our projectile is going to land, but we still need to know when to launch it so that when the robot reaches that impact point, we'll have our projectile will arrive at the same time. Well, the total time, the total travel time is similarly just T app plus T impact. And yes, we did guess that they were probably the same, but they don't necessarily have to be. And so this then was going to be 0.146 seconds plus 0.146 seconds. And so 0.146 plus 0.146 tells me that my T total, so my total in flight time was 0.292 seconds. And there we have it. So just summarizing everything that we've got here, this is what my robot needs in order to hit the target whenever it comes wandering by. Now, there's a lot of bookkeeping that has to be done with this. And as you see, we've been working on this problem almost an hour now. And really, it seems very, very complicated, and it kind of is. But if you are focused on one piece and you really deeply understand the physics behind each one of those pieces, then we can assemble it together and we can get our final answer from that. So that's why up to this point we've only been working in one dimension, because we need you to be able to see, okay, this is the physics behind that, because you have to know that cold. Now we're going to take that and we're going to apply it in all of these different ways so that I can finally get to the answer of one of these really complex problems. Now look on the last page. Here we're kind of summing up what to do, which I think is a really useful thing for you to have handy. It might even be worth putting in your flipbook for this. So we're going to draw that diagram so that we can see what's happening, because remember that when we drew our diagram and we launched our projectile like this, that was when we realized that I'm going from 0 to 0, from height 0 to height 0, and I've got no real way of doing that because nothing happens. So that was what made us realize that we had to break the problem into two phases. That was our next step. So in this case, we broke it into two. There may be more. It just depends on what's happening as things are going in there. All right, so as always, we break all of our vectors into components. So we get all of our initial vectors that we know. Not only the initial velocity here, which remember was Vm, but we also broke our Vap into components. And a lot of students forget that this actually has components. It actually has two directions. So it's 0 in the j hat direction, but it is not 0 in the I hat direction. All right, then we wrote our equations for the horizontal component. We wrote our equations for the vertical component. We got the final values for phase 1. We then took those velocity from the first phase to be the velocities for the second phase, and some heights and some times and things like that. Did the same thing again. Wrote the equations for the horizontal, the vertical, solved them to get the final value that we're looking at. And then this last part is very important. Analyze the results physically to ensure we're answering the question that was asked. And that gets into this idea of, let me put this in blue, of is this T impact and this is T app? Or is this T impact? Well, obviously T impact was each one of these halves, but we had this similar problem then when we were talking about our distance. Let's do that in purple. So the question then becomes, is if this is D app, is this D impact, or is this D impact? And we realized that we could do either one, that it simply depended upon how I wanted to set up the problem. So make sure that what you're doing makes sense physically when you're going with this. All right, so as you've seen, we've solved a very complicated problem. The projectile motion problem is actually fairly challenging. However, if you want your robot to hit a target, you're going to have to take these results and have your robot do all the calculations for you. Now, it's doing the calculations, but you're the one who's providing the engineering. You're the one who's figuring out what these equations are. Then the robot will use its sensors to get its initial data, and oftentimes, for example, it might find the distance, and then based on that, work it backwards so that we know the angle that we need to shoot at. So all of these things are available to you once you understand the basic technique for how to solve this type of problem. And yeah, there's a lot of steps, no kidding. But you do have to stay organized and you do have to keep up with your bookkeeping. So use that 5-step procedure. Divide your page into the sections so that you can follow everything that's going on. If you're just writing all over the page, it's going to be really hard to follow. On the other hand, if you're using, for example, engineering graph paper, you can block off sections for different parts, label what you're doing in each one of those sections, and you're going to find it much easier to keep up with what you're doing. We'll see you next time.